What do I do to the exponents? Yeah, what's 1/2 plus 3/2? 4/2, which is 2. Very good. So this becomes 3 to the 4/2, otherwise known as 3 squared, which is 9. And we usually start with numbers to get going on this before we start worrying about. Oh, that sneeze. We usually worry about the numbers before we worry about variables. Same thing here. 4 to the 3/2 quantity squared. Well, that's the power to power rule. What's 3/2 times 2? 3. And again, 4 to the 3rd, 64. Not too terrible so far. Same deal here. The quantity 9 times 4 to the 1/2 power means that you're just distributing the 1/2 power to both 9 and to the 4. What's 9 to the 1/2? 3. And 4 to the 1/2. Bless you. 3 times 2 is 6. Exactly. And I was just about to show, notice if you used order of operations tell you to take care of the stuff in the parentheses first, which was 9 times 4, 36. 36 to the 1/2 power is 6. So we mathed correctly. All right. Negative exponents, same deal. This is just like, I almost kind of wish we would have done this one yesterday the more I think about it, because you saw some of those properties thrown into it. 25 to the negative 1/2. Well, that 25 isn't happy. Where will it be happy? The bottom, denominator. Good. So that's just 25 over, 1 over 25 to the 1/2, which is 1/5. Playing war is where things get a little interesting. And this is where common denominators will come into play. Obviously, in this first example, it's 6 to the 5/2 over 6 to the 1/2. Who wins? 5/2 or 6/2? I'm sorry, 5/2 or 1/2? 5/2. So what will 5/2 minus 1/2 be? Yeah, 4/2, which is 2. Yeah, so it becomes 6 to the 4/2. There you go from there. Okay. It's nice when they have the same base. You can do these kind of things. And then the last couple the last one's also very simple. 8 over 27 to the 1/3 power. Again, that just means we're going to distribute, if you will, the exponent to both the numerator and the denominator. And you actually probably did this last year. Remember when you guys did similar volumes? You did similar areas, similar volumes, where you had to take square roots or cube roots and stuff? This is one of those things. Okay. So this becomes 8 to the 1/3 over, this up a little bit. You get 2 thirds. Not so bad. Well, it gets a little weird. In case you didn't figure that out already, you're all like, oh, this is nice. And then, stuff happens. For example, do these a little bit at a time. So we'll start piecing this together when it doesn't have common denominators, when it has extra things you have to do. Okay. 5 to the 1/2 times 5 to the 4th. Are those the same base? Yeah, they both have a base of 5. The exponent, yeah, the base is the value that's that doesn't have the exponent. What's being raised. So since you're multiplying, that means you have to add the exponents. Well, 1/2 and 1/4, that's fairly simple to do to get the common denominator. It would be 4, correct? So 2/4 plus 1/4 becomes 3/4. So this would just be 5 to the 3/4. Okay. The general rule for this stuff is, guys, that if they give you the problem to start in fractional exponent, your answer will be in fractional exponent. If they give you the problem to start in nth root, your answer will be written in nth root. Okay? It is always easier to do the math part as the fractional exponents because of the common denominator stuff. Then you just have to change it at the end. You'll just do a change into the nth root, excuse me, from nth root to rational, and then just go back. All right, and we'll get into that. This one. 12 to the 1/3 over 4 to the 1/3, all squared. Well, you start thinking about it. Can you rewrite that numerator to have a 4 to the 1/3 in there? Isn't 12 to the 1/3? Think about rules. What does that mean? What does a 1/3 power mean? What are you doing in terms of the nth root? It's a cube root, right? So when you go back to thinking about cube roots, or you go back to thinking about square roots, aren't they just products of roots? So couldn't you rewrite the cube root of 12? Isn't that the same as saying the cube root of 4 times the cube root of 3? What's that? It's a slight. Okay. The reason why I'm showing you this is because sometimes you can simplify it before you do other things. The rules of splitting apart nth roots are all the same. It just so happens that you guys have just done it only in terms of square roots before. It doesn't have to be just a square root. You can do it with any root, splitting it apart into products. It still means the same. Okay? So what I'm getting at is, excuse me, I could rewrite this as 4 to the 3rd times 3 to the 3rd over 4 to the 3rd. So now what drops? Yeah. What we're doing here is we're trying to figure out a way to simplify it before we go any further. Now you have 3 to the 1/3 squared. That's back to your power to power. So we just multiply. What's 1/3 times 2? 2/3. Okay. See how we're getting just ever so slightly more complicated? But yet it really isn't. It's just making you think about one little step. Going along the lines with that, put something separate one, more space. Can I go to a clean one? I'm gonna get out of there. 7 over 7 to the 1/3. They have the same base, don't they? They have different exponents. What's the exponent of the numerator? 1, right? Okay. How else can I rewrite that 1? Very good. I can rewrite that exponent of 1 as 3/3, can't I? 3 over 3. Same thing as 1, isn't it? What I'm doing here is I'm trying to create that common denominator off of it. Now I can play war. Who wins? The top, the 3/3. So what would your final answer be? 7 to the 2/3. Very good. Okay. All right. So far, so good. Now, when you think about some of the rules that we've had as far as square roots and denominators, were we allowed to keep a square root in the denominator? No. We had to rationalize. Remember doing that? So, excuse me. Let me just make something up real quick here. Let's say it was 1 over, I'm going to go to a variable for right now, just to, you would rationalize that. What would you guys do to rationalize that? Where? Top and bottom. Okay, cool. So what you guys were doing is you guys always multiplied by, basically, that's a factor of 1, isn't it? No matter what, you always, whatever it was, a number or a variable or whatever, we always multiply by the same thing over itself because it was just 1. We were just changing the shape of it. Now, think about that in terms of rational exponents. What's a square root as an exponent? It's a half, isn't it? So if I multiply the top and bottom by, what's 1/2 plus 1/2? 1. So what you're doing is you were, in essence, creating an exponent of 1 without realizing that you were doing it. Okay? You were doing that all along. And you would have that, or you would write it as square root of x over x. Now, do you think that's going to change at all if that's there? Yes, ma'am. I didn't hear that last part. So how many more would you have to add to it? Yeah, you're on your right. Yes, you were there, but you're saying just the yeah, exactly. So this doesn't change. What we do is we go to our nth roots. So if you think about it, we're going to be able to rationalize nth root stuff the exact same way, because we don't want to have fractional exponents in our denominator, because fractional exponents in the denominator are the same thing as having square roots in the denominator. It's just not proper math. So in this case, if you see something like this, I would always suggest to rewrite it as the fractional exponent, because you'll notice as you do more of these, working with the fractions is so much easier than working with an nth root. Because just like you were saying, how many more thirds do you need in this case to make a whole? 2. I need 2/3 top and bottom to make a whole. And that's how that would look rationalized. Now, the problem itself started as an nth root, though. So how do I rewrite that nth root in the numerator? Yeah, cube root of the quantity x squared. Oops, the quantity, I always say this wrong. The quantity cube root x squared over x. Okay. Yes, ma'am. I see where when you get to this part here, this equals 1. Okay, and I see where you're getting, because if you get it to here, then you get 2/3 and 3/3. You want to play war. Well, who's going to win? The 1/3. It becomes a 1/3. You wind up with that infinite loop. All right. With the fractions, it's really easy to get into the infinite loop. Like, when do I stop? When do I stop? Where do I go? And that's that's the weirdness of this style versus we just had regular square root, like the square root of 3. We had to multiply top and bottom by root 3. We'll get through this. All right. Not too bad. I start throwing a little bit in here for you. Okay. Product, yeah, we did this. We just did this. Yep, we did that. Never mind. So for example, again, excuse me. Same idea. Since these two guys have the same nth root, just put them together. All right. It was the same way that you did with square roots. If you had the square root of 2 times the square root of 3, it became the square root of 6. It doesn't change when you have a cube root. It doesn't change if you have a fifth root. Those rules, everything that you've learned about how to combine and work with square roots, or just only square roots, all of those rules apply to this. The only thing that's changing out in front is the nth value. That's it. So let's see. 4 times 16 is how much? Okay. Now let's think. Is that a perfect cube?
Yes.
What is it? And one way that you could have realized that is it 16 4 times 4? So you have the cube root of 4 times 4 times 4, which gets you. Okay. Same way with division. We have the 4th root of 162 over the 4th root of 2. We had one similar to that yesterday. We had 4th root of 81, and what's the 4th root of 81? 3. Yeah. So this becomes the 4th root of the whole thing, 162 over 2, which was 81. Oops. Remember, most of the root stuff that we're going to see are usually going to be small enough value that you shouldn't have a problem figuring out real quick. I think there were a couple yesterday that were a little weird. I think we had, what was it? Wasn't there like a 243? You might have had to think that was like a third of that, or fourth of that one. You might have had to do a little bit of thinking, but for the most part, they're pretty quick. Okay, they're pretty quick. If you know the basic cube roots, especially, 8, 64, 8, 64 to 81, and then if you know, wait, no, 64 is the cube root, 64 is the fourth root. Thank you. Yeah, I'm thinking 27. Yeah. Yes, it is. Right. I'm thinking. Fourth is 81. Yeah, I don't know where I got the 64 off that, and then it's a big number. 256. I knew that. What's the perfect cube hiding in the 108? We have what, 8? So as you get going right away, you've got 2 cube, 3 cube, 4 cube, 5 cube. It's 27. 27 times what? 4. So we have 3 cube root 4. Do you guys remember how we would search for perfect square roots in the calculator? We didn't use square root function, we used the table. You remember how we did that? So how do we do it? When we were searching for perfect squares, we took a number, we divided it by something. What did we divide it by? X squared, very good. So for example, if we did 12, we wanted to find out how do you simplify the square root of 12. Since we're not using multi-view calculators, because that would just say, oh, it's just blah, blah, blah. Here we had to actually do some thinking. What the calculator would do, it would pick all values of x, square it, 12 divided by it. And if it was a clean number, you knew that they would match themselves through. And what we did is we went to the table. And we're looking at positive value. So 12 divided by 1 squared is 12. 12 divided by 2 squared is 3. And then after that, it was all decimals. That meant when we looked at our calculator, that told us that the square root of 12 was 2 root 3. Remember how that little cheat sheet worked? You're looking? Remember, so I know that you know that the square root of 12 is the square root of 4, square root of 3. What's the square root of 4? 2. Okay, so what the calculator is doing is just taking values of x, and it's doing order of operations. It's picking what numbers work. 12 divided by 1 squared, 12 divided by 2 squared, 12 divided by 3 squared, and so on and so on and so on. You're looking for in the table, what's the last one before it goes all decimal? And it's just a little shortcut. It doesn't change if it's a cube root. You still do the same process, but instead of dividing by x squared, we're dividing by x cubed. Same thing with x to the 4th, x to the 5th. Any one of those, you divide by x, whatever nth root it is, and it'll help search for perfect squares to find the dump out. So if I look at that cube root of 108, I would do 108 divided by x to the 3rd. Same idea, go to the table, and it'll help me search for values. It's taking 108 divided by 1 cubed, 108 divided by 2 cubed, 108 divided by 3 cubed, and so on and so on and so on. The last value before it goes all decimal is the 3 and the 4, which means it's 3 cube root 4. Okay? It's a nice shortcut to simplify nth roots because the multi-view calculator, it won't even do nth roots. It only does square roots. It doesn't do cube roots or anything like that. This is a nice little trick to remember to help search for values. It's a nice little trick. Okay. So if you can't figure that out at the top of your head, yes, ma'am. It's part of the nth root. The answer would be 3 cube root 4. Yep. Mm-hmm. Yep. You get that. Let's see. Same, well, we just did the square root of 12. Square root of 12 was what? 2 or 3, yeah. Okay. 54. What's the perfect cube that goes into 54? We already said that wasn't 8, that was 56. 27. 27 times what? 2. So cube root of 27? 3. Okay. There you get that. All right. And now back to the idea of the denominator stuff. I have the 5th root of 3/4. Sorry. Now, what I want to do is, do you guys all agree that in somehow, some way, we're going to have to rationalize the denominator? You guys see that already? So I'm going to rewrite this as my first step in terms of fractional exponents. And I'm going to set the fraction exponent to both the top and the bottom, numerator and denominator. Okay. So I'm going to write this as 3 to the 5th over 4 to the 5th. How many more fifths do I need in the denominator? 4. Oops. Well, same base, different exponents in the denominator when I'm multiplying. I just add them. So 1/5 and 4/5 is 5/5, otherwise known as 1. Here I now have 2 different exponents, so I can't combine the base values to have that exponent together. So I just have to leave it how it is. But my problem itself started as nth root. I can't combine these two, so what I need to do is rewrite them as nth root. So I go back to the 5th root of 3 times the quantity of the 5th root of 4 to the 4th. That's the only rule. When you start as an nth root, you finish as an nth root. The mathing in the middle is just easier as a fraction. Okay? Wow, that's a lot. What? So let's try these. I'm pretty sure I have the PDF posted, but I'll make sure it's there. We'll go. We'll go by 3s. 12. Okay. It's about 2 to 3 of each style that we just did. All right. I think 12 is a good decent number here. All right. We'll give those a shot for tonight. Tomorrow we'll go a little bit further into this with the variables, and then turn them into just a giant blobs of fun. All right. $22, $25, $28, $31. Yeah, go by 3s. And I think it ends on 54. 25, 28, 31, 34, 37, 40, 43, 46, 49, 52, 55. Sorry. I think it's 55 it ends on. Yeah, that makes sense because that's 33 apart. This means that there's 12 problems. Counting. Yay. I know. Should make a shirt. Counting. She has such disdain for me. Bless you. Oh, hey, what we did here with Flex stuff, we decided to make our lives easier. Just so you guys know, if you need one, you come up here and say, oh, I'm going to grab this class right here. Oh, look, there's a little sign-out thing. You put your name and the date, put the card back in, take the class. When you come back in, you take the card out, and you put a little check mark next to your name, and you put it back here. So now we know who has all the passes and no one will lose them. I know, right? Every once in a while, we have a decent idea.